So let's go ahead and very quickly finish up the common collector amplifier stuff, finish up the parts that I said we would knock out today in a couple of minutes. That's exactly what we're going to do. All right, so I took the time to go through and break these things down. So for our amplifier stage, after I factor out our mid-band gain, it's going to look something like this. GM R naught in parallel with RE over 1 plus GM R naught in parallel with RE times RL times 1 plus GM R naught in parallel with RE over R naught in parallel with RE plus RL times 1 plus GM R naught in parallel with RE. So hopefully, very unsurprisingly, the voltage gain is still going to be something very close to 1, which is the absolute purpose of a collector follower amplifier. So our mid-band gain tells us that, our numerator is almost exactly the same thing as our denominator. And then we have this factor over here on the right-hand side, which is just this RL times this bit over R naught in parallel with RE plus the exact same thing. So both of these are going to contribute a factor that's very close to 1 overall to our gain. Can you refresh just what the reason is for this? What purpose of buffer amplifier? Yeah, so its job. From a voltage amplifier perspective, it is a buffer amplifier, so it has a gain of as close to 1 as possible. What its real purpose is to be a very good current amplifier. So when we used an emitter follower in our current mirrors, like its goal was to effectively leach a very, very small portion of the reference current away, amplify that current to provide the base current to the actual transistors in that circuit. So it's a very, very good job. It does a very, very good job of amplifying current and a poor job, I guess, of amplifying voltage, in as much as the output is always slightly smaller than the input. For our input stage, so I have this Zn here is equal to Z pi plus 1 plus beta Re prime. Just to be really clear here, Re prime is R naught in parallel with Re in parallel with RL. And then I'm going to introduce a base resistance just as a shorthand notation. That's nothing more than R sig in parallel with R1 in parallel with R2. So when we wind up expanding this out, substituting in for Zn and Zthev, what we wind up getting is 1 plus S times RB times Cn, all multiplied by R pi plus 1 plus beta Re prime plus S R pi 1 plus beta Re prime C pi. So our numerator is split up in such a way that we can easily get the 2 zeros from it. And then once again, our denominator is going to look like a second order polynomial in S. So AS squared plus BS plus C, where A is R pi times 1 plus beta Re prime RB C pi Cn. B is given by R pi times RB plus 1 plus beta RE prime. Excuse me, this should be C pi. I'm having a slight brain fart here, so let me explain. I have CN in here, but there should not be CN in this literally at all because we are looking at our high frequency transistors. So that is coming about from the ZN, no, because that's where the C pi is coming from. Everywhere that we see CN, actually that should be C mu because that's connected between the base and ground. Yeah, sorry. So all of these CNs should be C mus. My apologies for that. What I get for doing math early in the morning. All right. Plus RB times R pi plus 1 plus beta RE prime C mu. And I'll make that mu look less like pi. And lastly, coefficient C will be R pi plus 1 plus beta RE prime plus RB. Okay, so I didn't remember to make any notes out for this, but we can do it very quickly. So this is our direct analysis of the high frequency response. Once again, we can always estimate things by using our open circuit time constant method, if I'm remembering correctly. Short circuit time constant method is for low frequency, open circuit time constant is for high frequency. Okay, so open circuit time constant approximation. So let's look back up here at our original circuit and kind of see what we're looking at here, right? So we only have these two capacitances, C mu and C pi, so that should arguably make things a little bit easier to deal with here. So when we're looking at C mu, it is placed between the base node and ground. So it's going to see effectively R1 in parallel with R2 in parallel with R sig when we look to the left, and it's going to see whatever the impedance is looking into the base when we're looking to the right, okay? So we should have effectively something that looks like this. Right? So here's what does C mu C? So here's R1 in parallel with R2 in parallel with R sig. Here's the terminals of the capacitor. And then over here is Rn looking into the base, which is just going to be R pi plus 1 plus beta R not in parallel with RE in parallel with RL, and those two resistances are showing up as if they're in parallel. Right, because both of them share this top node and they all share the bottommost node with the capacitance. So we could say that R C mu is R1 in parallel with R2 in parallel with R sig. All of that in parallel with what I have listed as R. Easy enough. Now let's scroll up again really quickly and see what C pi is going to see. That might be helpful looking at our small signal model here, right? So with C mu as an open circuit, let me erase some of this stuff so we can kind of talk our way through this here. With C mu appearing as an open circuit and Vn being grounded out, we're going to have this R sig in parallel with R1 in parallel with R2 connected between the base and ground. We have that resistance R pi directly in parallel with the capacitance. We have an R naught in parallel with RE in parallel connected underneath. So let's draw this out here. Let me do it underneath here. What does C pi see? So here's that resistance RB. Here's our base terminal. Here's R pi. This is VBE. These are the terminals that we're looking in through. GM VBE. I'm going to put ground over here, and I'm going to attach RE prime down here. So this is about as simplified as I can make things. So I think actually test source method might be the best way to go about this one, right? We're trying to find that resistance scene looking in there. So the reason why I'm thinking about using a test source method here is because effectively that allows me to just set what VBE is. Right? So if I were to apply a test source here and find the current leaving, the ratio of V test to I test is what we're going to be looking for, right? Okay, so let me think about this really quickly. I'm trying to figure out where to do the KCL. Okay, so if we do KCL at the emitter, we have I test flowing out. We have GM V test flowing in, we would have V test over R pi flowing in. And now I need to figure out how to express the current flowing through the resistance RE prime. That RB, yeah, the RB being there is going to mess that relationship up, I think, right? Yep. So you're effectively saying, let's close this loop because those two grounds are together. Okay. So that would be the current. That would be flowing in though, right? Because so it's going to drive a current. If we treat that in that way, it's going to drive a current that's flowing this way. And so when we're looking at the emitter, it's flowing in. Okay. That seems reasonable enough. So V test over RB plus RE prime. And that actually makes things really, really simple, if that's correct. Yes, Ryder. So ground is one node. So I can tie those grounds together without any issue. The positive polarity terminal of V test is up here. The negative polarity terminal of V test is down here. So that resistance RB plus RE prime is effectively looking like it's in series, or excuse me, in parallel with R pi. So there's a total voltage drop of V test over those two guys. So that's why we put it over here and then divide by RB plus RE. And conveniently enough, all of our V test terms wind up on one side, I test winds up on its own side. So this is going to look like V test times GM plus 1 over R pi plus 1 over RE prime plus RB, which means RC pi is just R pi in parallel with the combination of RB plus RE prime in parallel with 1 over GM. Seems good enough to me, because I totally forgot to make this section. So we only had the two resistances. Now we have our two time constants. Apply the open circuit time, the open circuit time constant method and estimate the start of the high frequency response. Okay, so I don't know about you guys, but I'm tired of doing frequency analysis, so I want to just move on to bigger and better things, which is our feedback analysis stuff, the last module of the class. So effectively speaking, all the stuff that we covered for the frequency response was supposed to be the material for test 2. I absolutely understand that I have not even given you guys a single homework assignment. So what my intention to do this weekend is to give you guys a homework assignment on frequency response for common emitter and common source amplifiers, a homework assignment on the frequency response of common base and common gate amplifiers, a homework assignment on frequency response of common collector and common drain amplifiers, as well as the take-home test, all in one big package of bullshit. I know it's gross, and to make it due effectively at the end of the quarter. It would be better, that's 3 weeks away, so I think that's a reasonable amount of time. That being said, we are also going to have homework assignments on the feedback stuff that are going through as well. Yeah. Luckily for you guys, and also very much for me, I fully intend on teaching the feedback stuff exactly the same way I've taught it previously, which means I already have the homework and exams prepared, so I don't have to do anything new for all of that crap. So this last section of the class will hopefully appear like I have my shit together at least a little bit more than usual. Yay. All right. Introduction to feedback, design, and analysis. All right, so up until this point, all of the analysis that we've been doing has been with open loop amplifiers. We know from our exposure to operational amplifiers and all of that kind of good stuff that very frequently feedback is employed to do numerous things, such as increasing our bandwidth, increasing the linear operating range, and all of that kind of good stuff. We're going to learn about why feedback provides those behaviors here in the next couple of days, and then we are going to apply feedback to our transistor amplifier circuits to kind of see how that shakes out as well. So the first thing I'm going to hit you guys with, and you may have seen this before in your 321 class, and if you haven't seen it in 321, you'll practically definitely see it in controls if you happen to go into that, is a signal flow diagram for a feedback amplifier system. So over here on the left, I'm going to put a signal X sub S, where that X sub S is literally just meaning signal. This could be a voltage or it could be a current. Doesn't particularly matter in the grand scheme of things. Then we have a summer here. And then I'm going to have this arrow right here. And I'm going to put a functional block with the label A. So this functional block with this label A is representative of our amplifier. Put a node here because we're going to mess with it really quickly. Over here on the right-hand side, I'm going to have my output as Y. So before we go messing with things too much, I'm going to put a dash line here. You don't need to draw it because I'm going to erase it in just a moment. If we ignored everything to the left of that dashed red line, we would have an open loop amplifier, right? So we have some input signal flowing into amplifier A, and we're taking an output on the output side of the amplifier that we call Y. Feedback forces us to have this summer over here on the left-hand side so that we can feed back some portion of our output into the input signal. So I'm going to take some of my output signal here and feed this into a feedback network that I'm going to characterize as another functional block with some parameter K. And then the output of my feedback network then gets fed in as another input to my summer. So now we're going to describe some of the intermediate signals and all that kind of stuff. Okay. So this path up here is what's called our forward path, also commonly referred to as our feed forward path. And then this path down on the bottom. Have you guys seen this before? Is that why you're giggling? Yep, exactly right. Engineers are very lazy, as you see evidence of every day with me. So, yep, we have a feed forward path and a feedback path. So this portion right here represents our feedback network. This summer right here is called our return mechanism. Our amplifier is our feed forward path, or feed forward system. And then this node effectively serves as a sense mechanism. All right, so now let's introduce signals to this thing. Okay, so on the amplifier input side of things, we're going to have a signal called X sub I. Okay. This is very commonly referred to in control systems as an error signal. Okay. And it is going to be some combination of X sub S and our feedback output signal, which I'm going to call X sub F. And I'm going to label our signal X sub F down here, and we're going to give it a representation in a moment, right? I'm going to put a plus or minus sign on the summer on the X sub F side, our feedback signal side, because we could have positive feedback, which is whatever will happen if we add that to it, or we could have negative feedback, which is what happens when we subtract that feedback signal. That is literally all positive and negative feedback means in a signal flow diagram. If we add it to the input, it's positive feedback. If we subtract it from the input, it's negative feedback. All right. So this error signal X sub I gets fed through the amplifier. So it's going to generate a signal Y is equal to A times X sub I at this node. That signal gets fed down through the feedback network. And so we can say that our feedback signal is simply K, our feedback parameter, multiplied by that signal Y. And now we've kind of completed the loop and describe all of the different signals that are in. So now let's talk about what happens if we were to have positive feedback. So in a positive feedback system, a portion of the output signal is added to our source signal, which increases the amount of input signal seen by the amplifier, and that in turn winds up increasing the closed loop gain. So mathematically, we would have the relationship Y is equal to A times X sub I, or A times X sub S plus X sub F, which is the same as A times X sub S plus K times Y. Just simple substitutions there. Everybody okay with that small amount of alpha? All right. So we are going to define our closed loop gain, or our gain with feedback, as A sub F. And this is just going to be the ratio of our output signal Y to our input signal for our system, X sub S. And what we should find is that our gain with feedback A sub F is nothing more than our open loop gain A divided by a factor of 1 minus K times A. So what can we say about our closed loop gain, or our gain with feedback here? Always larger. So A sub F, yeah, will always be larger than our open loop gain A, because we have our open loop gain divided by 1 minus some fractional part of our open loop gain, right? So A sub F is always greater than A. Just to be clear here, A sub F is our closed loop gain, A by itself is our open loop gain. And so positive feedback forces our gain, our system gain, to be larger than our open loop. So in some applications, this can be quite good. In most applications, this is terrible. And the reason why it's terrible is because we don't always have a great amount of control over what our open loop gain is, at least in commercial products and all of that kind of stuff, like due to manufacturing tolerances and things like that. The open loop gain that we're going to get from our transistor-based circuits is highly dependent on whatever the temperature is, whether or not we have an unregulated versus a regulated supply voltage, so whether or not our supply voltages are constant, all of those kind of things impact our open loop gain. And so therefore, our gain with feedback varies widely with temperature, power supply voltages, all of that kind of good stuff. In fact, that's the principal drawback of a positive feedback system, is what's called gain instability. So I want us to very quickly here determine, and you guys are going to be so excited that you're going to get to see numbers today. Been literally months. I want us to determine the closed loop gain, A sub F, for a system in which our open loop gain A is 10 and our feedback factor K is 0.09999. So plugging in our numbers, nothing remotely wild or crazy here. We're going to have 10 divided by 1 minus 0.09999 times 10, which comes out to be 10,000. Why the K number was still going to be such a weird thing, because I want to get a nice even number. So we can see here that our closed loop gain is 1,000 times larger than our open loop gain, right? Now, I want to see what happens if we repeat this for an open loop gain of 9.9. So for an open loop gain of 9.9, what does that mean specifically? We have decreased our open loop gain by 1%. And I want to see how much our closed loop gain changes. Okay. So our second gain with feedback here is going to be 9.9 divided by 1 minus 0.09999 times 9.9, which comes out to be 900.819. So a 1% change in A yielded a 90.992% decrease in A sub F. So this is the principal drawback of positive feedback system. Even a very, very small change in our open loop gain yields a huge change in our closed loop gain. What if, looking back up here, KA is equal to 1? What would our gain with feedback be? Infinity. What does that imply? No input signal. Sorry, what was that? Unlimited power. Not quite. No input signal gives us some output signal. Literally, having no input signal whatsoever will cause us to have an output. Where have we seen that before? You guys remember the astable multivibrator circuit from circuits 2? We talked about when we were dealing with a positive feedback system. That's literally what this is, right? So effectively, positive feedback is really, really good at making oscillator circuits, whether or not you want it to behave as an oscillator circuit or not, right? That's what positive feedback is all about, is saying, I want to introduce the smallest possible change in my system and get the largest possible change in my output, which is really great when we want something to vary wildly back and forth between our supply voltages, but every other application, not super great. Yes. When you make an oscillator, clock circuits. Yeah. No, absolutely. That is the application for positive feedback, is clock circuits and all of that kind of good stuff. Which are super important, but not an everyday thing that we're particularly interested in with amplifier design. So let's instead look at what's going to happen if we have negative feedback. So in a negative feedback system where we're subtracting some portion of the output signal from our input signal, we would have the relationship y is equal to a times xi yet again, where xi can be substituted as x sub s minus x sub f, or a times x sub f minus k times y, and then rearranging to find our closed loop gain. This comes out to be a divided by 1 plus ka now, which means that AF is always less than our open loop gain. Exactly what we would expect for negative feedback and exactly what we've seen in literally all of our other classes, right? So when we were dealing with op amps, which had an open loop gain of roughly 100,000 or more, and we applied a negative feedback path by placing a resistance between the output and the inverting input, and then applied other little resistive networks, we largely found that our closed loop voltage gain was entirely dependent on the ratio of those resistances and had almost nothing to do with our open loop gain. It allowed us to establish what our closed loop gain is without ever having to actually know what the open loop gain is. So one of the biggest properties of negative feedback is gain stabilization, the exact opposite of what we saw in positive feedback. Okay? So let's just put here properties of negative feedback include gain stabilization, or also called gain desensitization. Sensitization. Noise or distortion reduction. Bandwidth extension. Input-output impedance modification. And I'm putting modification there specifically because, as we'll learn in a little bit, depending on whether our feedback network is placed in series or in shunt with our amplifier, means that our output and input impedances will either increase or decrease. So we can do either by applying negative feedback. And we should also see linearity improvement. So these are all different properties that negative feedback tends to give us. Yes. Why that it gives you an infinite output? What is the limiting factor? So you can't ever receive an infinite output signal because that would require creating energy, right? So the output is actually going to be limited by, so in the case of an op amp, it's limited by your supply rails, right? So your output signal can never exceed VCC plus or be more negative than VCC minus. So in a transistor amplifier, it will never get higher than VCC plus or more negative than ground because all we've ever been dealing with is single supply amplifiers. But we could just as easily make it a dual supply amplifier by just everywhere that we had ground, put that as VCC minus, and that would extend the overall range. So it's always going to be limited by our supply voltages. Can't get higher, can't get more positive than our positive supply voltage and more negative than our negative supply voltage, because that's the amount of energy that we're putting in, and we can't get out more than we put in. Kind of thing. All right, so let's work an example on the gain stabilization and desensitization. Effectively, we're going to do practically the exact same thing that we did a moment ago, but with a negative feedback configuration. So let's say that we want to find AF when our open loop gain is 10 to the 4 and our feedback parameter is 0.01. So we would find that we would have 10 to the 4 divided by 1 plus 10 to the 4 times 0.01. And this comes out to be 99.010. So much like we expected would be true, and actually part of mathematically proved would be true, our closed loop gain is less than our open loop gain. Now, where this gets interesting is what happens if we allow our open loop gain to change, right? So instead of having A is equal to 10 to the 4, let's rework it with A is equal to 9 times 10 to the 3, okay? So effectively, we are decreasing our open loop gain by a factor of 10%, right? Going from 10,000 to 9,000 is decreasing it by 10%. My mental math is working here, right? Our new closed loop gain is going to be 9,000 over 1 plus 0.01 times that same 9,000. Comes out to be 98.901. The change, let's call this AF1 and AF2, would be AF2 minus AF1 over AF1 times 100%, comes out to be negative 0.11%. So when we had positive feedback, we saw that a decrease in our gain of 1% caused a decrease in our open loop gain of 1%, caused a decrease in our closed loop gain of 90%. Here, we see that a decrease in our open loop gain of 10% caused a decrease in our closed loop gain of 1/10%, right? So our system gain is much, much, much more stable in a negative feedback configuration. So that is one very, very huge advantage of this. Now, we can actually describe this phenomenon as a whole mathematically and not have to go through this rigmarole every time if we were interested. Okay? So what we're going to do is we are going to take the derivative of our gain with feedback with respect to our open loop gain. So that gives us the derivative with respect to open loop gain of A over one plus KA. which using the quotient rule comes out to be 1 plus Ka minus Ka divided by 1 plus Ka squared, or simply 1 over 1 plus Ka squared. And we can rearrange some things. So DAF is dA over A times A over 1 plus Ka times 1 over 1 plus Ka. So just to be clear here, I've split my 1 plus Ka squared up into these two terms, and I've just multiplied both sides through by and then I'm multiplying and dividing by this same term. I know it looks rather odd, but what that allows me to do is express things like this. So I could have DAF divided by AF is equal to 1 over 1 plus Ka times dA over A. So I can now see that the relative change in open loop voltage gain is multiplied by a factor of 1 over 1 plus Ka to give me the relative change in my closed loop gain. So I no longer have to actually calculate what my open loop gain is for, or excuse me, what my closed loop gain is for two different values of my open loop gain. If I know how much my open loop gain changes, I now immediately know how much my closed loop changes. So this factor of 1 over 1 plus Ka is very often called our gain stabilization factor. So this is how much our gain is stabilized. All right. Got 20 minutes. Let's work. Look at one more property and we'll call it for the day. So let's look at that noise reduction property. So I'm going to describe a simple circuit. Okay. So here we have our input signal X sub S. I'm going to put a summer here. And I'm going to add to my desired input signal some noise. And then the sum of these two gets passed into a traditional amplifier circuit. And our output of this traditional amplifier circuit or open loop amplifier circuit is then whatever our gain is of our amplifier A times our desired input signal plus our noise. So effectively, what I'm trying to impart to you is that we have noise in addition to our input signal fed into an open loop amplifier. The open loop amplifier amplifies not only the signal that we want, but also the noise as well, which means the ratio of those two quantities is effectively a fixed thing, which, depending on what we're looking at, could be good, could be bad. Okay? So if X sub S is a voltage or, sorry, that's definitely of, not or, current signal, power delivered to an arbitrary load resistance RL would be given by the following relationships. So our input signal power would be A times X sub S squared divided by RL. Although I guess realistically, that would only work for a voltage signal, because if it was a current, it would be times RL. But anyway, let's just say voltage here. We know that from literally circuits one, power is proportional to the square of the voltage or the square of the current. That's what I'm getting at. If we looked at our noise power, we would have a similar relationship, right? A times X noise squared over RL. And so we can define a signal to noise ratio, SNR, as the ratio of the signal power to the noise power, which is just going to come out to be XS squared over X noise squared. And in decibels, this would be 10 log our signal to noise ratio, or 20 log XS over X noise. So there's different ways of expressing that. All right, so we've covered here what our noise and stuff and comparing it to our signal looks like for an open loop configuration. I hear whispers and stuff. What do I need to clarify anything? Okay. And then James and Lucas, do I need to clarify anything to you guys? Okay, yeah. So I can go in a little bit on that. So signal to noise ratio might be a concept that you guys are not yet familiar with, but it's definitely something that you will deal with in your professional careers, particularly those of you that go into research and design and all of that kind of good stuff. So a signal to noise ratio is really exactly what the name explains. It is a ratio of the signal power to the noise power. So a good signal to noise ratio or a high signal to noise ratio means effectively that the signal that you're trying to extract is much larger in magnitude than your noise signal, so it's easy to see things. So let me explain graphically what something with a good signal to noise ratio might look like. Okay. So we might have something like this, and this is me trying to draw a sinusoid, which you guys know I'm terrible at. So something like that, okay? So you can definitely see that there is a sinusoidal signal there, but there's variation around it because there's noise on it as well. So that would be a relatively good signal to noise ratio because you can absolutely distinguish the actual signal of interest from the noise that is superimposed on top of it. A bad signal to noise ratio would be where you absolutely cannot see what the actual desired signal that you're trying to amplify, measure, etc., is because it's buried underneath all of the noise. So for some applications, a signal to noise ratio of 1, where the signal power and the noise power are literally equal, is perfectly okay. Other applications, particularly say biomedical devices and all of that kind of stuff, where it literally means the life or death of somebody because you're trying to measure some signal with reliability, you need a much higher signal to noise ratio so that you're guaranteed that you're not making a medical diagnosis off of literally thermal noise or Brownian motion of electrons in your sensor, right? So anyway, that's signal to noise ratio in a nutshell. On the left-hand side, you can actually see that there's a sinusoidal signal. On the right-hand side, it's the hottest of garbage because it's really, really noisy. Okay. So let's look at another signal flow diagram where effectively we are going to apply not only feedback, but also introduce a very low noise amplifier stage. So we're introducing a stage specifically such that our noise isn't going to be too overwhelming. Okay. So here's XS. Here's our summer. Here's our amplifier A2. I'm going to put a little note here. Low noise amplifier. Here's our summer, another summer. Here's our noisy signal corresponding to our noisy amplifier A1. And now we're going to feed back from this output Y back to our input signal with some feedback system K. So let me describe why we might set up a situation like this. So a low noise amplifier or high precision amplifier is designed in such a way to provide that as its defining characteristic. So it probably doesn't actually have a particularly good voltage gain or anything like that. If that's what we're interested in doing, boosting the signal, it's just really good at providing some level of amplification without adding additional noise. So we might use a low noise amplifier as an input stage, feeding that into a traditional amplifier which has a much worse noise performance characteristic in order to get our overall voltage gain that we're looking for. And then we're going to find the application of this feedback path K will reduce the overall noise power in our system. Okay, so that's what we're talking about here. Multi-stage amplifier, and then using feedback on the system as a whole to reduce the noise power seen at the output or the noise power referred to the input. So I'm going to define some signals here. So let's call this signal right here X2, which is just the input signal for the amplifier stage A2. Let's call this signal X1, which is just the input signal for the amplifier stage A1. And we'll call this guy right here XF, which is just K times Y, and this represents our feedback signal, right? So, and specifically here, I'm going to introduce a minus sign so that we're dealing with negative feedback. All right, so we can see, I hope rather easily, that our signal X2 is nothing more than XS minus XF, which could be written as XS minus KY. Are we all okay with that? So X2 is the output of that summer. So XF is getting added, XF is getting subtracted, as indicated by the signs, the polarity signs on our signal flow diagram. Kind of like applying Kirchhoff's current law. Signals flowing in must combine to get signal flowing out, and then the polarities tell us whether we're adding signals or subtracting signals. Okay, just in case you guys aren't super familiar with signal flow diagram, yeah, which I have no idea because I don't know what the hell Amir's doing in his classes. All right, so the signal X1, which serves as the input signal for amplifier A1, you guys tell me what that's supposed to be. So A2, X2 plus X noise. Absolutely right. And what would our output signal Y be? A1 times X1. So let's do some substitutions here, right? So our output signal Y, A1 times X1 would be A1 times A2 X2 plus X noise. Substituting in again for X2, we would have A1 times A2 times XS minus KY plus X noise, like so. And now I could rearrange this to find that Y is going to be XS times A1 times A2 divided by 1 plus K A1 A2 plus X noise times A1 over 1 plus K A1 A2. So this part right here is our desired output signal. And this part over here is our contribution from our noise. So let's look at what's happening to our desired output, right? So we have A1, the open loop gain of our noise amplifier, times A2, the open loop gain of our low noise amplifier, divided by a factor of 1 plus A1 times A2. So we're still getting some gain, but it's lowered because we have negative feedback. For our noise, we have A1 by itself divided by that same denominator. Which means the gain that is the closed loop gain that is applied to our signal XS is larger than the voltage gain that supplies, larger than the closed loop gain that supplies to our, that applies to our noisy signal by a factor of A2. So we get a significant stronger desired output than we have our noisy output by introducing a configuration like this. So that is how negative feedback can be used to strengthen the signal. So let's look at what's going on with our signal to noise ratio. So the signal to noise ratio with feedback is going to be our input signal power. So this would be XS A1 A2 over 1 plus K A1 A2 quantity squared divided by X noise A1 over 1 plus K A1 A2 quantity squared. Very obviously, these common denominators cancel each other out. And we're left with XS squared, hold on, let me see, divided by X noise squared times a factor of A2 squared, which is just our signal to noise ratio without feedback boosted by a factor of A2 squared. Expressed in decibels, this is nothing more than 10 log SNR sub F or 20 log A2 times XS over X noise. Yes, Ben. So 10 log is when we're dealing with power. 20 is when we're dealing with voltages or current specifically. So if I have X squared, when I'm dealing with a power, I can pull that 2 out to make that 10 20 effectively what's going on. So anytime that we're dealing with power, it's 10 log blah blah blah. And anytime we're dealing with just the signal itself, it's 20 because the power is proportional to the signal split. So still exact same fundamental definition. It's just we use 10 when it's power, 20 when it's the signal power. All right, it's 10:45, so we're done for today.